Okay, so Assalamualaikum and good morning everyone. Okay, so previously we have learned a bit on some applications of differentiation. Okay, so we have covered rates of change. Okay, now we will go into velocity and acceleration. Okay. Okay, so velocity and acceleration. Okay, so if a body moves a distance, okay, so here we have distance equal to x, okay, f of t, okay, and then we have velocity v. Okay, so v is a change of distance over time, so it is also known as dx over dt. Okay, so we differentiate distance x over t over time. Okay, and then for acceleration, which is a, equal dv over dt, which is a change of velocity over time. Okay, so meaning here we differentiate second times dx over dt. So we have a equal to d to x over dt squared. Okay, so let's see some example. Okay, so here we have distance x meters, okay, moved by a car in a time t seconds. Okay, so it is given this function which is x, okay, distance is equal to 3t cubed minus 2t squared plus 4t minus 1 meter. Okay, so we have to determine the velocity and acceleration. Okay, for when t is equal to 0 second and b when t is equal to 1.5 second. Okay, so what we do is, okay, so we write again the distance, okay, which is x equal to, so distance, okay, we have distance, okay, x is equal to 3t cubed, okay, minus 2t squared plus 4t minus 1 meter. Okay, and then velocity, which is v, okay, is equal to dx over dt. Okay, so we differentiate x over t. So we have 90 squared minus 40 plus 4 meter per second. Okay, because we differentiate over t. Okay, and then for acceleration, which is a, is we differentiate second times d2x over dt squared. Okay, so we have 18t minus 4 meter per second squared. Okay, because we differentiate over time, second time. Okay, so then let's see for a. Okay, so a, what is a and v? Oh, sorry, v and a. Okay, when t is equal to 0. So we just substitute t with 0. Okay, so v is 9, 0 minus 4, 0 plus 4 meter per second. Okay, so v here is 4 meter per second. Okay, for a, okay, substitute t with 0. Okay, so 18, 0 minus 4 meter per second squared. So we have a equal to minus 4 meter per second squared. So negative means it is slowing down. Okay, or also known as deceleration. Okay, now we go for B. Okay, so B, what is A? B and A. Okay, when T is equal to 1.5 second. Okay, so V, which is previously we have 9. Okay, T squared, T we replace with 1.5. Okay, square minus 4T, okay, which is 1.5, and then plus 4. Okay, so we have V equal to 18.25 meter per second. Okay, and then for A, we have 18T. Okay, so 1.5 minus 4. So we meter per second squared. So we have A equal to 23 meter per second squared. Okay. Okay, so next application in differentiation is turning points. Okay, so turning points here is P and Q. Okay, so turning point. Okay, turning point. Okay, so Q is turning point as well. Okay, so now let's look how we determine the nature of turning point. Either it is maximum or minimum. Okay, so we look at P first. Okay, so we can see that, okay, so the gradient before the turning point P, okay, before, which is here, it is going upwards. So it is positive gradient. Okay, and then after passing the turning point, okay, so it is here, it is going downwards. So it is negative gradient. Okay, from positive to negative. Okay, so turning point P is, we call it, is maximum. Okay, maximum turning point. Okay, so we can see, okay, it is appears like, okay, it appears as the crest of a wave. Okay, the top of a wave. Okay, and then let's look at Q. Okay, turning point Q. Yeah, so for turning point Q, okay, Q is turning point. Okay, point. Okay, and then let's have a look the gradient before turning point Q, which is this the left side. Okay, so we can see it is going downward, so it is negative gradient. Okay, after passing the turning point Q, the gradient of the graph is going upward, so it is positive gradient. Okay, from positive to negative, so the turning point is minimum. Okay, minimum, and you can see it appears as bottom of a valley. Okay, so this one is minimum turning point. Okay, the Q. Okay, and then, okay, so it actually possible, okay, if the gradient on either side is same. Okay, okay, in this case, okay, we see that, okay, there is turning point here, which is turning point also means that dy dx is equal to 0. Okay, so turning point, okay, so dy dx is 0. Okay, it is 0 here. Okay, 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 so this is the turning point. Okay, but what happened if the gradient is same? Okay, so we can see before the turning point, okay, the gradient is going downward, so it is negative. After passing the turning point, the gradient is still the same, which is going downward, so it is negative. So we call this as points of inflection. Okay, same goes to the right side. Okay, this one, before turning point, it is going upward, so it is positive. Okay, and then after passing the turning point here, the gradient is still going upward, so it is still positive, the same. So this one here also is turning point, points of inflection. Okay. Okay, now this is the procedure, okay, to find the stationary points or turning points. Okay, so we will be given y f of x, okay, function of x. Okay, then we determine the gradient, which is dy over ds. Okay, now we know that stationary points, okay, maybe, okay, this is the stationary points or turning points, okay. So dy dx here is equal to 0. So, okay, so then let, okay, dy dx equal to 0. And then we can find the value of x. Okay, then once we find the value of x, we substitute into the original equation. Okay, yf of x to find the y coordinate values. So then we can find the coordinate of turning points. Okay, and then after we find the coordinate of turning points, okay, then we have to determine the nature of stationary points. Either it is minimum or maximum. Okay. Okay, so there are two ways, okay, we can use to find the minimum or maximum points. Okay, first is we substitute, or first is we just do the second differentiation. Okay, and if the values, okay, is positive, then the point is minimum. Okay, if the value is negative, the point is maximum. If the value is 0, the point is point of inflection. Okay, the second method, okay, second method is we determine the sign, okay, of gradient just before and just after the stationary points. Okay, let's say for, let's say we find the curve, okay, the gradient of the curve, okay, maybe, okay, like this. Okay, so if it is positive to negative, okay, like this, positive to negative. Okay, so the point is maximum. Okay, so the point P here is maximum. Okay, what if we find that the gradient is negative to positive? Okay, in this case, this is negative, okay, and then going past just after the turning point Q, it is positive. So the point is minimum. Okay, so Q here is minimum. Okay, and if the gradient is same, okay, before and after, let's say positive to positive or negative to negative, the point is point of inflection. Okay, so let's see some example here. Okay, so locate the turning point on the curve y equal to 3x squared minus 6x. Okay, and determine its nature. Okay, determine by examining the sign of gradient on either side. Okay, so this is the first method, the second method. Okay. Okay, so now what we do is we have to find dy dx. Okay, so y is given 3x squared minus 6x. Okay, so now we want to find the turning point coordinate. Okay, so turning point, so we know that is dy over dx is 0. Okay, turning point gradient. Okay, and then so then we have to differentiate y over x. Okay, so we have 6x minus 6. Okay, and then we let equal to 0. Okay, so we have 6x equal to 6. So x equal to 1. Okay, so now we want to find the value y. Okay, we want to find the coordinate y. So we just plug in x into the original function. Okay, so y is equal to 3x. Okay, 1 here, squared minus 6, 1. So we have 3 minus 6, which is negative 3. So the coordinate of turning point okay, is 1, negative 3. Okay, so now we want to determine the nature of, determine its nature. Okay, so now, okay, by examining the sign of gradient. Okay, so turning point is 1, negative 3, right? Okay, so just before turning point, okay, gradient, okay, just before x equal to 1. So we let x equal to 0.9. Okay, so dy dx, which is 6x minus 6, right? Okay, then we just 6, okay, substitute with 0.9 minus 6. So dy dx, we will get negative 0.6. Okay, so this one is dy dx here is negative. Okay, negative. Okay, now we determine gradient just after turning point. Okay, so x is 1. So let x is 1.1. Okay, so dy dx is 6. Okay, x we replace with 1.1 minus 6. So we will have 0.6. So it is positive. Okay, dy dx after turning point is positive. So it will be like this. Okay, so this is turning point. Okay, before dy dx it is negative. So the gradient is negative going downward. So this is negative going downward. And then after turning point, the gradient is positive, meaning it is going upward. So positive. So this means the turning point here is minimum. Okay, is minimum. Okay, so let's say we want to determine through the first method, okay, which is we differentiate second time. Okay, let's say the first method. Okay, first method, which is d2y dx2. Okay, second differentiation. So dy over dx is 6x minus 6, right? Okay, so we differentiate second time over dx. Okay, so we will get 6. Okay, so it is positive value. Okay, so when it is positive value, okay, which means okay, positive. So the point is minimum. Okay, so the answer is same. Positive, so the answer is, the point is minimum turning points. Okay, so this is it for turning points. Okay,